Welcome to this explainer. Okay, today we are tackling something absolutely fascinating. We're looking at a paper that asks a wild question. What if we could just let physics natively do the math to solve modern AI's massive energy problem? The concept is called attention by synchronization in coupled oscillator networks. It's this brilliant, mind-bending blend of artificial intelligence and physical dynamics. And man, I am so excited to break this down for you. So here's our roadmap for today. We're going to hit the AI energy problem, computing with physics, anchors and oscillators, testing the theory, and finally, the future of edge AI. It's going to be a fun ride transitioning from traditional computer science, taking a little detour through nonlinear physics, and landing on a hardware solution that could literally change the game.
All right, part 1, the AI energy problem, or hitting the memory wall. Every good story needs a villain, right? But the villain here actually isn't the AI model itself. No, the real problem is the hardware, our standard chips that are just bleeding energy, shuffling data back and forth all day.
You know, you might be wondering, why exactly can't your smartwatch or a tiny environmental sensor run a full transformer model like ChatGPT without dying in literally 5 minutes? Well, it all comes down to the attention mechanism. That is the core of modern AI. It has to constantly compute similarities between every single pair of tokens in a sequence, and as that sequence gets longer, the computational cost just skyrockets quadratically. It's brutal.
And you can really see this stark contrast here. On one hand, we've got the digital standard, the softmax function. It is incredibly power-hungry, demanding massive mathematical exponentiation and heavy memory traffic. But on the other side, physical oscillator networks. They don't even do arithmetic. They literally just settle into place through natural physical equilibration. Imagine a ball naturally rolling to the bottom of a bowl. It finds the answer using almost zero power. Moving on to part 2, computing with physics and building a hybrid pipeline. So how do we actually merge a highly complex AI model with, physical springs and pendulums? Well, it starts with a hybrid setup. First up, we use a standard digital front end to handle the initial token embeddings, basically turning our data into vectors. And from there, it calculates what we call coupling weights. You can think of these weights as basically deciding how stiff or loose the invisible springs between our data points are going to be.
Next, we hand that data straight over to the physical oscillator network. And this is where the real magic happens. The heavy lifting, figuring out which words actually matter to each other, is computed entirely by just letting the physical system equilibrate. The oscillators just push and pull on each other based on those springs until they find a stable consensus. Literally no floating point math required. How cool is that?
Finally, we bring a digital back end back into the mix. It reads those settled physical positions using a super simple affine normalization, basically just a quick scaling adjustment. It measures the physical angles, or cosine similarity, of those settled oscillators, and boom, we completely bypass that massive, power-hungry softmax math, but we get the exact same attention weights out the other side.
Okay, part 3, anchors and oscillators. Let's look at math as a physical reality, because to really wrap our heads around this, we need to visualize these abstract math operations as actual physical objects.
Now, what's really wild is that this consensus behavior that we're desperately trying to build into AI is something physics has been doing natively forever. It's described perfectly by the Kuramoto model from way back in 1975. Fireflies flashing in unison, pendulums syncing up on a wall. Nature knows exactly how to find consensus.
So translating this to AI transformers, you've got queries and keys. Picture the queries as fixed anchors locked in place on a sphere. And the keys, they're free oscillators being pulled along the surface of that sphere by our invisible springs until they reach a natural balance with the anchors. That final resting place, that is your attention calculation, perfectly solved by pure physics.
Let's hit part 4, testing the theory. The theory is elegant, sure, but we need empirical proof. Can physics actually go toe-to-toe with digital math in the real world?
Well, when researchers tested this on a grammar task, subject-verb agreement, the physical model, using incredibly simple two-dimensional oscillators, didn't just match the digital baseline, it actually beat it by over 5 percentage points on hard sentences. And get this, the digital model had catastrophic training failures in 1 out of 5 runs. The physical model, 0. The geometry of the sphere actually acts as a natural stabilizer. Incredible.
They also tested it on an audio task, keyword spotting. And again, it outperformed the digital baseline. But here's the absolute kicker. The researchers completely froze the value projections, which is usually a huge part of how the AI actually learns. Even frozen, the accuracy barely dropped at all. That absolutely proves that the physical dynamics themselves, the actual springs and anchors settling into place, are doing the cognitive problem-solving here, not some hidden digital trick. Now, I gotta be honest, there is a slight catch. It's called the dimensional bottleneck. For simpler tasks like grammar or spotting keywords, those 2D oscillators work great. But if you want to run massive, complex, large language models, a simple 2D circle just doesn't have enough geometric room to express all those intricate attention patterns.
But the fix is actually pretty straightforward. We just scale up the dimensions. When we move from a 2D circle to a 4D, 8D, or 32D mathematical sphere, that performance gap between physics and digital math just vanishes, following a totally predictable power law. Give the oscillators enough dimensions, and they match the digital superpower flawlessly.
All right, bringing it home with Part 5, the future of Edge AI. We're looking at physical AI substrates, because at the end of the day, we are talking about a total hardware revolution here.
Because we aren't just theoretically simulating this. The whole point is to physically build these chips. At a 2D level, you only need a handful of oscillators per attention head. Imagine embedding AI natively onto microscopic vibrating mechanical structures or electrical LC microcircuits. On those physical materials, the energy cost is tied purely to the device's physics, completely unbound by those old von Neumann limitations. The energy savings are just off the charts.
To be clear, the goal of this explainer, and the paper itself, isn't to say, software is dead. Softmax is still incredibly optimized for massive cloud servers. The real objective here is to provide a mathematically grounded blueprint for accurate attention on physical materials. It's an entire blueprint for the edge. So I want to leave you with this to ponder. If we can literally encode the hardest, most computationally heavy part of artificial intelligence natively into the physical syncing of microscopic pendulums in circuits, computing it for virtually free, how completely does our world change when powerful AI no longer even needs a battery? It's wild to think about. Thank you so much for joining me on this explainer. I hope this sparked as much curiosity for you as it did for me.